Okay, so it's recording and then, okay, let me share my first OneNote. Okay, so my OneNote is visible, right? Yeah,
Yeah, it's
okay, yeah. So, hello, hi, welcome all. And this is one of the session, a book club of CTCI. And today we are going to discuss trees and graphs. Okay, I think we already had some of the problems already discussed earlier in some session by Ayush. But I think let's go of all of those problems. Some of them will be repeat, but it's fine, right?
yeah.
Okay. So the first problem here is 4.1. It says route between nodes. So there is a given directed graph. Design an algorithm to find out whether there is a route between two nodes. Okay, so this is a very simple problem, right? It's like you are given a directed graph, and then you need to find a route if it exists between the start and end two nodes. Okay,
Yeah.
yeah. So the way actually it can be done, I think everyone knows. Most of us are aware of it. Like we can only use two of the graph traversals. One is either DFS or other VFS, right? And then both have their pros and cons. The DFS implementation is simpler, uh, but the only problem is that traverse whole node's path, as what says in this book, and then in some cases it might end up going through all the nodes, right? While BFS is a bit of more code to implement, but it actually is more efficient if you want to find a shortest path between two nodes, right?
Yeah.
So this is simpler and very generic, yeah. So I'll just quickly run through the code, right? So okay, so this is the code what was in the book also. Okay, so this is okay. Actually, the book you has used most of the time. The book actually does modularization. They have all the functions separately written and everything well done. So I think I'm trying to follow the pattern. So it makes more sense during an interview. Also, in some cases, we are supposed to do all that, right? Not just write the code. So they actually it was shown like you have an enum. You set an enum for a state of each node. It will be unvisited, visited, and visiting. Okay, and then this is the housekeeping of graphs and all that.
I think code is not visible. Are you sharing?
Oh, it's not visible?
No, I think that one note is there.
Really? Okay, did I not? So now is it unshared?
Yeah, one note is unshared.
Okay, okay, let me know. Are you able to see it now?
Yeah, no, it's visible.
Oh, thank you. Sorry about that.
Yeah.
Okay. So, as was in the book, as I said, they have maintained a state of each and every node as an enum. So, three states are already defined: unvisited, visiting, and visited. Okay. So, this is the node of a graph, and then this is a graph class. This is all about the housekeeping of a graph. And here is the actual algorithm of the search, which uses BFS. So the three parameters, one is a graph and then the start node and the end node. Okay, if both of the nodes are same, you return true, or else you start with a queue, and in the queue actually you start with a you use a type node. So and then whatever the nodes are from the graph, actually you assign first actually initialize all of them to unvisited, and then push the start node, okay, and make that as a visiting. Okay, and then look here the normal BFS. You look into queue and pop the first element, and if the first element is not null, and then go to all its neighbors, right?
Okay.
And when you go to the neighbor, then you see if the neighbors are unvisited. And if you find the end, you return true here, or else you keep on adding them in the queue and change the state to visiting. And here, when you're done with a particular node, putting all its neighbors, then you make that visited. Okay, so this is the way it is followed in the book. So an extra step, what usually we don't do is have the state defined when we really want to write a well-maintained code for a production and all that stuff, right? So this makes more sense. So that is what
So
actually was in the code. Yeah, go ahead, Shashank.
I'm saying in directed graph, we always have these three states. I mean, unvisited, visited, and visiting. Even in that, we had problem on lead code where course schedule was the right topological sort. That is also directed graph only, right? So
Yeah, that is
we have
true.
three state: process, processing, and processed.
Yeah, that is actually a good way to do it. But usually we tend to do a very quick way instead of setting all the states because we think all the details are not so much required, right?
Yeah,
And then we usually skip that, but it's good, always good to show this.
all the
I
time.
also like it. But when you are in a hurry, if you want to explain the crux of the whole algorithm, so that is what we follow. But this is the right way. What you say is correct. Yeah. So yeah, so this is the very simple thing, and that's the only one algorithm what is described in the book. But they say you need to actually discuss the trade-offs between BFS and DFS with the interviewer and all that stuff. Okay, so that is always good. Okay.
And union find shouldn't be used. I'm just asking, like, I think will it make any sense here? I don't think, right?
Well, to find a path between two nodes, um, the quickest would be these, BFS and DFS. But
Yeah.
union find, I think you should be able to do it, right? Because if
Because DFS we are using, right? Wherever
yeah,
we use DFS, we can use union find. But
yeah, so it should be like the same, you actually go through the, you unite two of the nodes when you start from a node, right? And then go to its all neighbors, and then you start uniting them, make a union of those nodes, and then keep doing that. So when you're done with all your dependencies, then you can look for the start node's parent and the end node parent. So if both are same, then you can say it is connected. Correct.
yeah.
So that way, yeah, I think we should be able to implement. Yeah, that's also one way to do. But only the thing is, it's not a shortest path. Like so, shortest path is always good with the BFS, right?
DFS, yeah.
Yeah. But also, yeah, that is one way of doing it. Absolutely.
Yeah.
So, okay, so I will just stop this sharing and then move to again my OneNote, and this will be okay. So now there were another couple of problems between 4.1 and 4.4. One was a minimal tree, and I thought it was very normal, which we have been doing it. So I did not include that. Okay, so it says like if it's a given a sorted array with unique integer elements, write an algorithm to create a binary search tree with minimal height. So that's very generic problem, right? So not included in our SD skills also, but it's very easy to follow. And the second one was of the least of depths. The third one, sorry. Given a binary tree, design an algorithm which creates linked list of all nodes at each depth. And it was, I think, similar to a BFS where we do a level order traversal and then create a linked list at each and every level of the BFS tree. Yeah,
Yeah.
so that was also easy. Yeah, so I just skipped those two and then came to this check balance. So this one actually, it says implement a function to check if a binary tree is balanced. And for the purpose of this question, a balanced tree is defined to be a tree such that the heights of the two subtrees of any node never differ by more than one. So it can be 0 or 1, right? If it is more than 1, actually it's not a balanced tree. Okay. So then what is the best way you feel, or maybe if you have read in the book, um, so what are the approaches one would go through? Any?
I think. If you start from leaf node, right, from bottom to top and check if that particular subtree is balanced or not, left subtree, right subtree, what is
Mm-hmm.
the difference between them?
Mm-hmm.
Because if that is in imbalanced, then entire tree itself is imbalanced, right? So bottom
Right.
up approach, from bottom to root you proceed.
Correct. Correct. Yeah. Absolutely. That is a good way to do. And but then how do you reach the bottom if you are given a route at the start?
Then you'll have pre-order you do, like hit till the, or post order you do, and post order you start from the leaves, and then for
Mm,
the, or while doing the recursion itself, roots left, left, left. You once you reach roots left, you
mm-hmm.
take its height and then roots height, right height, and then check the difference of that. If the difference is more than one, return falls to the above one, right?
Right. 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 Yeah. So I think you use the very optimized way when you said it's a post order.
Yeah.
Yeah, that's the very um, efficient way of doing it. But in the book, actually, they have described two approaches. One is recurse the entire tree, go to each and every node, okay, and at each and every node, just check, compute the height of the both the subtrees of that particular node, okay.
Yeah.
So I think they have followed the first approach like a sort of a pre-order, okay. And then when it is done, if you look at the approach, it, because you go to the each and every node, and then you go to its left subtree and right subtree to find their heights, so that itself will be a log of n operation, and then
Mm.
you have to visit each and every node, so it will be n, so therefore the time complexity will be n log n. That is what they say, okay. So the height is calculated for each node, therefore, okay. So I'll quickly go through this. Okay, man, what happened here?
I thought we are visiting all the nodes one so off and
Right, right.
okay.
So what you said was the efficient way, but as per the book, they have described both the approaches, right? So I'll first go with the first approach, and then we'll come to your approach.
Yes.
Okay. Yeah. So this is the approach one, and this is our function is balanced. This is a function signature where we pass in any of this root node. Okay. And so when we pass a root node, first we look if it's a null, then we return true. That's the base case. And then, or else for every node, first I calculate the height and just look for what is the difference, height difference. Okay. And if the height difference is greater than one, I don't have to do anything, immediately return false. Or else in a sort of a pre-order, right? I just go again, recurse for its left and right subtree, and then return from there, whatever the values will be. But if you look at the get height, is again the similar function. It goes, it takes one of the node, and then again recursively goes to its left and right subtree, okay, and then it calculates the height, okay, by incrementing one. And so whatever is the maximum value of the height of a left or right subtree, and one will be the current node, right, what you are in, then you
Mm.
return the height. So if you look here, actually each and every node, it is going uh, both the left and right subtrees, finding the height, and if you find the height is okay, then again go to the root of left and right of the root, and then keep doing this in a recursive way. So therefore, the algorithm says it's n log n, right?
Yeah.
So
Mm.
the next best algorithm, what you said was this one, like the approach two. It says check if the tree is balanced while computing the height. So you don't have to compute the height when you go to each and every node, but you can actually compute when you are computing the height itself. You check if it's balanced. That makes more sense, right?
Yeah.
Uh, Therefore, the time complexity is O of n, but you have a space complexity, which is the height of the tree. So that is very efficient, right? In the space as terms of space as well as the time complexity. Okay, so I will just go through this algorithm here, and this is what was the approach, right? So what it says is this is, it checks the height. If the height is I'm returning height as whatever, it's an integer value usually. If it's not equal to int min, this is just a base case. Okay, and then you return that I found a height which is balanced, right? So the way it is done is this check height actually is a single recursive function. It goes in here, it checks height of a first finds the height of a left subtree, and then finds height of a right subtree. Okay, and if both of them are not int min, okay, so int min actually will come here. So when first you find the difference both of them, and then if you just look for its absolute difference, if it is greater than 1, okay, then it is not a valid one, right? Therefore you return int min.
Yeah.
Yeah, or else actually you just do a max of right left plus 1. Yeah, so here actually the way you are saying, it's like a post order, correct?
Yeah.
And you just find it. So this is the most efficient way of doing it, and I agree.
So suppose the left high and the right high is different. It's one different, right? Is
Mm-hmm.
it? And then the max will be, oh no, let me think. Um, let's say the high is one more than left,
Mm-hmm.
then we're gonna return the right high plus one,
If
right?
so, okay. So what are you taking as a left height? Maybe it's 3, and then right
The
height is
right
2,
four,
4.
yeah,
3 and 4. Okay, so then your 3 and 4, your height difference will be 1, correct?
okay,
Mm.
Okay, so your height difference is 1. So you are not returning minus 1,
yeah.
right? So then what you're going to do is you're looking for whatever is the maximum
Maximum.
height, and then you add that 1.
So the difference will be five, 3 and
5,
5.
right? Yeah.
So if it's 3 and 5, then okay, and you return 5 back. Okay,
Yeah, I written 5 back, but then again you come here, okay? So then you go to check for the other ones because it's recursion, right? So you keep on doing for every node, right? So until and unless you find if you are within the range, okay, or if you're not within the range, immediately it's going to return from here because you are going to return int min, okay,
okay,
or else you're not going to calculate at all. The way Shashank was saying, right? You go to the leaf always,
Mhm.
and then first find actually the difference between the leaves, and then keep on going to its parent, 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 and whenever you see if there is an imbalance, then immediately return int min, or else you keep on checking for each and every node, and if there is no imbalance, then at the end actually when you come here, so it's going to show some value. Okay, it's not going to show int min, it's going to show some value which will be more than 1, correct?
Mhm.
That is
it
what
looked
it
like, initially it looked like it two, let's say when I return the max, that would be two different than the other one, but actually it's not, because plus one is the current node, right? You
yeah,
plus
yeah,
one because it is
great.
up the current node. Yeah,
Mm-hmm.
yeah, that makes sense.
Yeah. So actually at the end it's going to return the actual height, whatever the height of this root will be. So what is the max height looking at the right and left? So it's not going to be 1 or 0, something like that, but it's going to be a bigger number if the tree is larger, right? And then if it's obviously it's not going to be int of min, so it will be a positive value. Yeah. So yeah, it's slightly cleverly written, looks very easy here, but you know, but I like the way Shashank actually analyzed it. First, do a post order, that makes sense. Then, if you think that way, actually, slightly is better.
Easier.
We can actually, analyze it. Yeah.
Yeah, and the book, it always, I mean, it normally it emphasize on reduce redundant work, right?
Yeah.
Now, if we look at the previous solution and this solution, we see in the previous solution we do a lot of redundant work, because
Correct.
you check the root and you come down, and check the root children, right?
Hmm.
And
Hmm.
keep checking a lot of redundant work there.
Yeah.
That's why we get n log n.
Right. 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 Yeah, that's a good observation. Yeah, yeah. Yeah, but to start with, I would say if there's something which comes, and usually the tree problems are very tricky. They look very easy now, but if you get something like this, yeah, if we don't recall this very optimized version, but at least we could start with saying, okay, now if it's balanced, let me find the height of the both subtrees here, then take a difference. Okay, then I look for it's greater than one. But then after that, what I do? Okay, then I again recurse. Okay, so at least maybe that is slightly, the way we write an algorithm or think an algorithm immediately, right? And then you can actually go and optimize this way. Yeah, I agree. So this is, so there are a lot of redundancy here, so you can actually remove those. Yeah, yep, that's nice. Yeah. Okay, so I will move to the next problem, and so the next problem actually, okay, okay, there is one more. It talks about valid BST, which is the 4.1, and it says implement a function to check if a binary tree is a binary search tree. And I thought that this problem is well known for all of us, right? We either go in order traversal or whatever the way we want, right, to find out whether it is a valid or invalid binary search tree, right? So
Yeah,
therefore I did not take that here, right? I think that should be okay, because those were more simpler. And but they have given a lot of other stuffs also in it. Maybe if in case we need it, we might take that in a next session or so. So I will jump to this one, and this is about a build order. And I really like this way, the way it is done. It is even this build order, even if it looks a very normal solution, and we have been doing it for a long time now, and we all know this algorithm also. Like a build order, usually it is a topological sort, right? Yeah.
yeah,
Yeah, so it says you are given a list of projects and the list of dependencies, okay, and all of the project dependencies must be built before the projects, okay. So so when he says list of dependencies, says the second project is dependent on the first project. So in this case, if B is the second project and A is the first project, so you need to actually build A first, okay, in order to actually build B, right? So that is what it is about, what is talking in this problem. And then you need to return a build order. So what is the best build order you want? And as yeah, so we all know about doing this. Other than topological sort, I don't think so. There is another way to do it, right? So in topological sort, there are two ways to do it. One is the BFS and the other is the DFS. So both approaches have their own way of implementing, and both are efficient. Correct. I think the time complexity and the space complexity of both of them should be almost same, right? In this case. Yeah.
Yeah, that's in the book, right? But there's one more. It's called what can can can
Khan's
algorithm.
algorithm.
Is
Yeah,
that?
Khan's algorithm.
Yeah.
Oh, but Can's algorithm is a BFS.
Yeah, kind of.
Right, right. Yeah, but
But there
I
is a
right.
little bit difference, right? I mean,
Uh,
it's BFS only, yeah, but
yeah, but okay. Now, if you look at this, that's very interesting the way you guys said, because if you look at the book's implementation, it doesn't look like that. It's okay. I'll just quickly show you. Um, but okay, this is done. Let me share my background and this. Just a minute. I'll open this way. Okay. So okay. So why I'm saying it BFS and the cans is almost the same, but the way it's implemented in the book is slightly different. And always they give more stress on as the modularization and everything is neatly done. I like that. So let's walk through all the code what they have given here. The first, the thing what is done is they have created a project class. Okay, in the project class you will have everything. So what you will have a name. Basically project is nothing but a node in our case, right? So they are given a name, okay, and then you have the children. So it's like the dependency or the neighbors, so neighbors will be stored here. But when you have a name, okay, you need it to be associated with a node, correct? So therefore you have an unordered map for here. Okay, so any name actually is associated with its this project object. Okay, and then if there are dependencies, it keeps on incrementing. So this is one actually I thought the dependencies are like we do in cans algorithm, right? The in degree. Okay, so they have used this independencies in this class itself. Okay, and then this is a very uh, simple constructor. You just pass on the name, you just assign the name, that's all. But then when you add the neighbors, okay, so you look in the map, if you find the neighbor already, if it's not, then you push this current node as a children, and also you assign that string, okay, with the node, with that node. So what you're trying to do here in this map, you're trying to only store the string which are the in the children. It's not this project. So project will only have a name here, but whatever the neighbors are, their strings and their project objects, they are stored here. That's what done here. And then this is what is the increment dependencies, which is used for a in degree, means incrementing it, and decrementing when you want to decrement them. And these are the helper functions, like you return the name of this current node, or you return the children, or you return the dependencies. Okay, and then if you look at this graph, this is what the main class is, where you have a project. It's an array of dynamic array of all the projects what are stored, all the nodes you can say. So that what the name is also. And then you have an unordered map where you have a string in the project wherein actually you store each and every node with its object, address of that object. Okay, so whenever you first create a project in a graph, okay, you assign just a name, and this will be actually looked into this map. If it is not there, then you actually assign that project name, and then you push that in the nodes also. So it's just building the nodes, right? Or at the end, if you usually, so this is a function which is used to create a node as well as to return the node if it's already there. If it's already there, you just return the name, go to this map, find a name, and then you return the object. So that's very simple thing. And then when you have to add an edges, so usually it starts from here. So you look for, just pass on those two names, and then you get its node objects, and then you actually assign, because if you start is nothing, start add neighbor is actually called from the project. So this is what it calls here. Okay, so this function it calls, and then this add object is added, and this is another helper function at a graph level where it returns all the nodes. So now this is the function build graph. If you it's almost a CAN's algorithm, but it's it, very differently implemented with all more functions, and to keep it more modularized. So if you have a build graph, actually, then you first you assign the projects, which is a vector of string, because that is what our function is, right? Or input to our example is. We are given a string of all the projects first, and then we are given an array, two-dimensional array for all the dependencies. They are also string. So this is what actually we are is given to us. Then we create a graph, okay, and then all the nodes are created first, and then all the dependencies are also assigned, and then the graph is returned. So this is the build graph. And then when we do this build graph, we need, and yeah, this is where actually the whole CAN's algorithm comes here. So here you actually order the projects. Okay, so but basically it starts from here. That's a find build order. First you have to build a graph, and then you actually do the topological sort, where actually order projects is nothing but a topological sort, where it takes all the nodes of a graph, and that is passed as an input parameter here. Okay, and then first this is sort of, I think, like a visited array maybe. Okay, so we are just assigning creating array first, and then this is add non-dependent. So add non-dependent is a function wherein we actually first look oh sorry, this order is nothing but a queue. Okay, so instead of queue they are using a vector over here, dynamic array. And so add non-dependent is actually you look into all the dependencies, like the in degree what we look in, and if the in degree is 0, Okay, so you assign all those projects, right? So therefore, that is what is add non-dependent here. You first, this is a queue actually. You fill in this queue by looking at the projects, and this is your offset. Initially, your offset will always be 0. Okay, because it's an array and it's not a queue, so you need to have an offset. Okay, from where you want to start. So this is 0th position you're starting. So you start filling in, look for each and every project. Okay, and then you look if it's in degrees 0, and then this order um, uh, array, we are actually filling in this order array based on the offset, adding it, and then you're incrementing the offset, return the offset here. So this is the queue. First you fill initially when all the in degree is 0, and then there is another variable which is to be processed, and I think the to be processed is used for to find if we have a cycle in a graph. Okay,
Yeah.
right, yeah. So then if you see to be processed, if it's lesser than an order size, which is all a order size, nothing but the size of a projects, right? All the nodes. And then you go in this order, this is our queue. So you just pull out one of the project. And if you see if its current is null, you return here. So that is what the cycle is, right? Or else you go and look for the children's, that is the neighbors of that particular this node's children, and then you go through each and every child of that particular or the neighbor of that particular current project, and then they decrement the dependencies. And as soon as you decrement dependencies, you will have some of the nodes which are free. Okay, then you again run the add non-dependent, so wherein you will add a more number of projects to our queue, correct? And then you keep on incrementing this because you already completed one of the project, right? So therefore
Yeah.
you are incrementing to be processed. And here in turn you are actually also adding all the order, you know, so that this is what going to be our output, right? So when you keep on adding them, and then when you come here at the end, you know what your order will be, and if you return that order, okay, so that will be our order. And then this will actually come out from this build order, this will be written from here, and this is the main key function actually does here. Okay, so find build orders, you written the projects, and then I'm printing it over here. So if I run this, so if you look for the 4.7, it will show all those dependencies. Yeah, so this is what it actually shows here in our. Okay, so yeah, it won't be exactly the same because as long as they have a topological sort, it's fine, right? Because the book shows it is FE or EF, both are fine, right?
Multiple answers. Yeah.
Yeah, you have multiple outputs, right? So this was one way. Okay, so it's almost like a Kahn's algorithm, but it's not very evident, right? Looking at the whole project.
Cool. Yeah.
Yeah. And the second approach, what is discussed is about the DFS.
Yeah. Using stack or normal flickers.
Uh, okay, so let's go there. So yeah, actually, I used exactly the way in the BFS. I use the array. I think Java use array, right? So most of, but C++ will all have a queue. We can I could have used a queue also, but I tried to maintain the way it was in the book. Okay, so but that was also not a bad implementation, right? So yeah, in this actually, um, yeah, it's the same thing again. If we look at here, okay, so okay, let me first run through, then we'll come to see whether it is a stack implementation or not. So here he's using all the states, okay, and then you have a project, the similar class, but I'm just renaming it to project 2 because I already have a project class already implemented here. It's almost same, but here there are some more additions, I think. Mm, like the get state, okay, and the set state. These are the two additions over here, okay, which were not there in the previous one. And then this is the graph. The graph is almost same, it's nothing different, okay. And this is the build graph. So build graph is actually doing taking all those string of projects and the dependencies and then creating a graph class, an object of that class. And then here, yeah, actually The order projects, it comes here. Yeah, it is using a stack. Shashank, right.
Yeah.
So the find build order actually first builds a graph using a build graph 2, and then order projects actually takes all the nodes of this graph, okay, and then it starts here. Okay, so here, so this is a stack, okay, the DFS, and then whatever the nodes what we are passing, the projects which we are passing here, for if it's not visited, okay, then you do a DFS, okay, and when you are doing a DFS, you return false, then you immediately return here, or else you return a stack, because it returns a stack with all the projects, and then we have to print those stack, right? So if you look at the DFS, okay, so this is the DFS. So it takes a project and then it takes the stack, and if each and every project state is visiting, it will return false. Correct, because usually when we enter here, we see if a project is not visited, and then we enter here, okay, and then when we enter here, and if we find that the project is visiting, this means that we are in a path, okay.
Cycle, I think. That
Yeah,
will also
there's
take
a
more cycle.
cycle
Right?
on there.
Yeah. So we are in the path, and then we have already visited this particular node, and then we are again coming here, so it becomes a cycle.
Yeah.
Correct. Yeah, what you guys have said is correct. And then, or else if it's not visiting, then you obviously it will be not visited. Then you set it to visiting, and then you keep on looking for its all children's, right? And then when you look for each and every children, again you do its DFS. But if you find if it is false, okay, so you immediately return from that. Correct. So
Yes.
the false will be here, right? So if it is a cycle, then it doesn't make sense going ahead. So you just return from here and then and get out of the whole loop. So because cycle. Or if it's not cycle, then you set the state to visited, and then you push it into a stack. Correct. And then at the end you return it is true. Yeah. So this was the whole yeah, the DFS implementation. And yeah, you are right, Shashank, it uses stack. I am not sure whether they have used the same in the book. Are they using a stack? But I use the stack because it looked easier for me to. Uh, okay, let me quickly check that. Um, yeah, they are also using a stack. Correct. Yeah, correct. So yeah,
Where do you set the visiting state for a node?
visiting.
Yeah.
Is
Initially,
that
you
in
set
Yeah, you're. I'm setting it to visiting here.
Oh, okay.
Yeah.
If
So
it's
if it is
not
not visited,
visiting,
then
you
yeah.
set it. Okay.
So initially it will be not visited,
Mhm.
and that will be initialized when you create a graph nodes, and then whenever you come here, you set it to visiting here, right? And then at the end, when everything is done for a particular node, when we have done all the recursion of that all its neighbors, then you set it to visited, right? Yeah,
Okay.
yeah,
So let's say if you have R node, there's no dependency, then you keep setting the visiting, and then you skip the for loop because there's no children, and then they said that you visited. Yeah,
yeah, yeah.
right.
yeah.
If
So,
you don't have any neighbors, then you have to do that, right? Because you've
I mean,
already visited.
when there is no dependency, at last we mark it as visited. Like this node is finally processed.
Yeah, yeah, yeah. But I really like this way because if you follow all the things in the book, I know this DFS implementation of a topological sort is easy, but if you don't follow all of these things, right? One is the cycle, correct?
Yeah.
And then these two parts, then actually you can be very, in a stressed out environment, you might make some mistakes, right? So it is always better to follow a
These
path,
three states
right?
are fundamental
Yeah.
always.
yeah, another thing is uh, visiting is only, let's see, visiting, you see visiting is only if if the node is currently on the stack, right?
Yep. Yep.
But if, let's say, if you already done with this, let's think about like connected component. We should not think about, but yeah, let's think about, we have two connected component, right? And then first we process the first connected component. When it's done, okay, and then we go process the second one. So the second one never see the visiting state of the first connected component.
Right. Right.
Yeah.
So this visiting will be for only those nodes which are on the function stack, not on this stack.
Yeah.
Yeah. So if it's on a function tag, it will always be visiting, and therefore, whenever we hit another same node as a visiting, it means that in the same function path which we are actually exploring, and therefore it is a cycle. Yeah, that makes sense. Okay. So, and then I think I will move to the next problem. Oh, there are some chats.
Yeah, book he was asking
Okay, okay,
Corman.
no problem. I think you're taking care of that. Thank you, Shashank. Yeah. So I actually was looking through all the problems, but or actually SD skills talks about only 4 problems, right? So I thought this problem is also interesting. One is about, and we have also been doing this in our lead code.
Yeah.
So this is about, designing an algorithm, uh, actually basically finding a first common ancestor. Okay, it's an easy one, but I found they have explored all 4 approaches here, and thought maybe just take this and discuss it here also. So what it
So
says, design, yeah, sorry, go ahead.
no, I'm saying, is this first common ancestor from bottom or from top?
Okay, yeah, okay, I think let's discuss what it is, then
Okay,
we'll,
okay.
we'll get to your question. Okay.
Yeah, sure.
So he says you design an algorithm and write a code to find the first common ancestor of 2 nodes in a binary tree. Okay, so you are given 2 nodes in a binary tree, and then you have to find the common ancestor.
Yeah.
Yeah, so it can be anywhere, I think. No, so
But
either
if
the
it,
root can also be one of the node.
okay.
Yeah, so we don't know actually. So it's just given that we are given 2 nodes in a binary tree, and then we have to find its common ancestor. So there are different flavors of it and different approaches, and I think they have covered most of them. But some of them actually in the lead code also are there. So maybe we can discuss that too. And he says avoid storing additional nodes in a data structure. Okay, this is not necessarily binary search tree. These are the 2 things what said. Okay, avoid storing additional nodes in a data structure. Okay, maybe I don't know. So what it means is you don't use any other data structure like a map or so, because that would be also easy, right? If you are given 2 nodes, and then if you have to find, you just run through a route if you are given a route. Okay, but let's see what it says in this approach. One is he says, okay, so book says that for a binary search tree it will be easy, just compare 2 node values with the subtree and return when they diverge, right? So if the tree was a binary search tree and we are given 2 nodes, we just start with the root and keep on comparing both of these, and as soon as both of them are not on the left side, or usually it will be earlier on the left side or the right side, both of them together, but in at some point of time, when they diverge, both of them are in different branches, it means that is what actually is our common ancestor point, right? And then we return it. So that will be very easy to find in a binary search tree. So if you look at the approach one, what it says that with links to parents. So there are different what you say variations in the problem what is created here. One is, you have now, imagine that you have a tree node which has a parent as a attribute also. Okay, so for each and every tree node we have a left and right only, right? But in this case you also have a parent, so every node will point also to its parent and also to its children's. So that is what it says. So when you have a link to the parent, so it becomes like we had that intersection linked list problem, right? It's almost similar to that.
Yeah.
Yeah. So that problem actually, okay, let me share the code. Okay, I think we are done with this one. Okay, yeah. So in this, okay, so what, okay, now if you look at, so this is what the tree node is. We have a left and right tree, and then we have a parent. This is one node, and this is our value, and this is our constructor, and then, so this is what the main function, entry function is. So we are just given p and q. We are not given anything else. Okay, we are not given even the root, and then we have to find a common ancestor. So the way it can be done is, first you find the depth of p, and then the depth of q, and then you find a delta. So now it becomes like a linked list, right? If we have a pointer to parent, so if we start from this p and then go to its parent, then you will go to its null, right?
Yeah.
Because when you reach to root, right? Yeah. So then we can actually just treat this as a linked list. And for that, if we do a depth search, not the traversal, but yeah, it's like you do the parent, and then you find what the depth is of both of them, and then you find the delta. And then if you compare, if the delta, whatever is greater, okay, so whichever the string is greater, and here I think they have taken this second to be the greater one. Okay, so you just assign the biggest string to one, maybe second, and then you move the string by that much delta. Okay, so now both of them are pointing to the same height, right? And then you can just use a while loop and then keep on incrementing both of them till you don't find the common ancestor, right? So what is depth is there's nothing but actually just goes in here, and then you have a depth as a attribute here, something variable, and then you keep on looking if it's not null, and then keep on pointing to its parent, and then you find how much depth is till the root, right?
Yeah.
So that looks very straightforward, and it's like a linked list problem now, correct?
Almost similar. Yeah.
Could
Right.
you annotate what it looked like? Because I haven't visualized it.
Okay, so if we annotate something like okay, now let me use this. Okay. So if it is like, if you have some string like 1, okay, 2, oh sorry, I should draw a tree, right? Okay,
Yeah.
so if this is 1, okay, this is 2, and this is 3, right? This is 4, so this is 5, and this is 6, this is 7. Okay, so now I am given 7 as a q, and 3 as a p,
Okay.
right? So now I can also go this route, because I know I have a parent pointer also here, right? So I'm using that property here. What I'm doing is I'm starting from p, okay, and jumping from year to year and year. So now my depth is 2 in this case, correct? But in this case my depth is 1, 2, and 3. Okay, so then I find the delta between 2 and 3, which is 1. So q is bigger, right? So then I assign q to second, okay, and then my p will be to the first. So what I do is, till I don't reach 2, I just push my p, go up, sorry, q. So then I push my q to here, okay. So now both are at the same level too, right? And then I use this while function, correct? So for this
Yeah.
while function, now I keep on incrementing one at a time. As soon as I hit a common ancestor, then I come out of this while loop and return this one.
Yeah.
So this is a CA.
But I mean, for 3 and 7, this is the common ancestor. This can also be one of them first, but this is the first one, right? Two, and one is the
Correct.
second. It depends whether we consider from here the first, top to bottom, or from bottom to top.
Well, you have to consider a common ancestor, which is the closest one, right?
Okay.
I know whatever you can have on the way up, but then always you will return a root, right? So root will always be a common ancestor for each and every one.
Let's say, I mean, one more something like here is there, and then this is not the root, right? But still,
Yeah,
this
then
is
you
the
will have to
common
still go
ancestor
one
for.
more. Yeah, yeah, agreed, agreed. But will still not root be, yeah, in this case also, why not? Because even if you have something here, so the
Yeah.
common ancestor for this also can be here because they both are on the left side still. That's fine.
But this is the third common, I mean, third common ancestor, right? If you go from bottom first, second, and then top is the third one.
Yeah. But usually common ancestor is always
Yes.
considered one which is the first diverse
Point. Okay.
bifurcation of these two trees, right? So
Yeah.
that is what is considered. Yeah. Yeah. Okay. So this was the first approach, and now they have many approaches. Okay. So the other approaches, what they talk about, I'll quickly run through all the approaches here and then come and show you the code. Other is another with a link to the parents again. Okay. But if you see here, actually it says that the time complexity is very good, right? It's O of D, where D is the depth of the deeper node. And that is very good, what you say, time complexity. But if you look at link to parents in this case, okay, so let's go back to the code, and I will show you what I mean by that. So it is slightly variation of the top one. Okay, so what it does is here in this case, we are given a root also. Okay, and then we are given parents of these two. Okay, and then P and Q. So what we need to do is, so first you have to find covers is nothing but actually it takes a root and it tries to find if P is there, and same thing it does for the root with the Q. Okay, so if it is not there, then it will return null itself, because if the P and Q, either of them, they are not in the root, it doesn't make sense to find a common ancestor, right? So what
Yeah.
does this function does here? Yeah, actually, if root is null, it will return false, or if root is equal to P, it will return Q, sorry, true, or else it will go to its left and right subtree and keep on finding for that particular node. Okay, so that is what the covers does. Okay, and there is one more function it looks for is a sibling tree, a sibling node. You pass on any of the node and then you try to find its sibling. So the way you can do is, because we have a parent, right? The parent pointer, you can go to its parent and then you can find which is my sibling, because I know what I am currently. I either maybe to a left or right, right? And then if you just compare my current with my, if it's on left, then I just point my sibling to the right, or else I'll point it to the left, right? So that is why the way I get a sibling, because I have a parent pointer, so I can easily find a get sibling also. And then when I'm done with this covers, okay, but in this case, if I find P and Q in the covers itself, okay, then I return P. Or if I find in Q, when I'm trying to, I take a Q and try to find P, right? So then I find P also, therefore I will return Q. So these are a sort of base cases, correct?
Yeah.
Or else then I go and find a sibling and then its parent, okay? And then keep on going in this while loop. So take a sibling and then try to find the Q always, right? Because I'm actually looking for P's parent, right? So then I keep on finding it, and if I again update my sibling and parent, as soon as I am done with this, I'm not able to find, right? Then I return my parent, and that would be my common sister. It's a similar implementation, almost same, but here it's slightly different way of doing it, because you are having a root also, and then you are taking help of that. But I don't think so that this has a very good time complexity, right? Because actually we are always going through its siblings and then finding a parent and then keep on jumping, right? And always looking, going, this cover actually goes through the whole subtree, so many of the time we are actually going through the whole subtree. Okay, so that, but I think they just mentioned here we can actually have another approach also, we can have a different implementation, when we are given a root also. And in the previous one, there was no root, right? So,
Yeah.
but I like this algorithm, this implementation. It's very easy, neat, and very quick. Also, correct. But this was one also discussed in the book, and maybe it might be useful in some other cases, right? So, but it talks about it's like it's a best worst case runtime. To some extent, I didn't understand what that means. Okay,
Okay. Yeah.
right.
What,
So, but it
what
says
is the purpose of finding the sibling?
the purpose of finding a sibling is actually because you are going to take the sibling and then you're going to find the other node. So because you're taking a sibling of P, correct? So you should have in the sibling you should have a Q. Then only you can say your parent is the CA, correct?
Yeah.
So for your parent to be a common ancestor, you first go to your sibling
Mm.
and then you keep on going up that way, and then you'll find it. So, but the time complexity is O of t, and when t is the size of a subtree, so that in case worst case it might be O of n also, right? Okay, now I'll just not go back to the one node, but there are other two approaches where it says that you don't have a parent at all. Okay, now this is a normal tree node. So what do you do? How do you do that? And I think that is what we have discussed also earlier in our lead code, right? Many of times we are not given a parent node, but if we are given a parent node, that's very easy to implement. So we had two approaches. Here actually we don't have a parent now. We just have a normal tree node. It's not the tree node 2, which was a custom one. So we are given a root and then we are given a P and Q. So how do we find out? So this is a cover function, the same to that. But here in the cover function, what you do is you recursively go to its left or right subtree, okay, and then you try to find the one of the node what you're looking for, okay. So if you find it, okay, if you find it here, then you return true or else you return false. So if you have a parent, you will do it differently, but if you don't have a parent, you can still find it, but you will have to go to the subtree, deep into the subtree, and find out if there is that particular node. So what it does here is actually, if because it's a recursive function, like it will keep on coming here. So the base cases will be if the root is null, you return the root, or if the root is p or it is root is q, then you return the root. That is what you want to write. Okay, and then the best way would be take this q and then you find out if uh, go to the root left and then and you try to find p, and then you assign it whatever the status is, like p is left, and then for you do the same thing for q also, go to a left only of a particular root, and then you try to find. So now based on these two states, we can find out if both of them are actually true. Okay, it means it is a both of them are in a on the left side, right? So it means this is not a common ancestor. The root is not a common ancestor, right? So for us to find a common ancestor, both should not be true. One should be true and other should be false. So it means that one will be in the left subtree of a root and other will be in the right subtree of a root. So that is what the definition of common ancestor will be, right? So if we see here, if P is left is not equal to Q is left, it means that is what a common ancestor, you return true. And if it is not, so it means that either or both P and Q are in the left subtree or they are in the right subtree. Correct. So for that, then what you have to do is actually use find out where your trees are lying. Okay, because you have to go again down, right? So if they both are lying, if our P is left, now we have checked the condition if they are not equal, but if it's not this case, then we come here, it means P is left is true either or it will become false, right? So if it is true, it means that our whole P and Q both are in the left subtree, and therefore you assign this as a root, okay, child side, okay, or you or else assign a right, and then you do the same thing recursively by as reassigning the root as a child side. Okay, so because now the root will be either a root of left or root of right. So we actually want to explore the left subtree or the right subtree. So then you just add that over here and then recursively keep on finding. And then you keep doing this until and unless the P left and Q left both are not same. Okay, so that is one way of doing it.
Okay, can we go? Can we? In the covers function,
Mhm.
it only return true if the node is on the left of the root, right?
No, either side.
Either side,
Yeah,
yeah.
left side of the root.
So because it compares for the left as well as the right.
But does it where it say only return true if the node on the left of the root?
There
No.
could be one node is exactly the root, the other is on left side, or one node. Three situations will be there, right?
Yep.
Yeah, that means if
Even,
it's on the right of the root, we should return 4, right? On the, in the
but
cover method.
but if the other node is on the root itself and next node is on the right, that is also a common ancestor, right?
No, I'm talking about the function on line 989.
Okay. So this one actually, what is this function? You try to, this cover function is going to find whenever you pass on any node. So if you are passing a node here like root, then it's going to look in this roots subtree and it's going to try to find if you have a q in it, sorry, p in it, right? So what it does here is it goes and looks in the roots left subtree and it tries to find if we can get a p, right? So how can that can be done? So you can do it by that our pre-order, right?
Oh,
So
okay, got it. Yeah.
yeah,
So you pass in the root left only.
yeah,
I see. That's the trick.
yeah,
Okay.
yeah, absolutely. So yeah, either if you just pass root left and right, then it will mess up. So you
Okay.
always pass root left, both of them, and just try to find if p is in the left, also q is in the left, right? So then it makes very things very clear. If both are true, it means that we are still have to explore more and we have to go deep down, okay, in the
Right.
left subtree, unless and until both are different. So when they are different, then that is the common ancestor. Yeah. So I like this approach also, and it's not a very difficult one to come. And then there is a fourth approach in here. It's about the same when we don't have parent, right? So it's slightly more implementation here. So this is what it is. You have a root, and then you have p and q, and then they are using a helper function. Okay. So, but actually returning some class object called result, which has more than one, just returning a tree node. Okay. So it looks, there's a Boolean flag. If it's an ancestor, then you return the node. So I'll come to that result class little later, or maybe I'll just quickly show you. So this is the result class. It actually has a node and then it has also a Boolean variable, which is ancestor. So if it is ancestor, this will be true. And also the node will be assigned always. So what it does here in the helper class, you are given a root as well as a p and q, correct? So then you look for the root. If it is null, okay, then you just return an initialize class where the node is null and then it's false. But if your root is p or and root is q, okay, so that means this is what your RCA is, common ancestor is, right? So therefore you return the root along with saying that my is ancestor flag is true, or else the same way what we did earlier, right? So, but here there is slight variation. So you first go to the left subtree of the root, okay, and then you look whether if you are able to find P and Q, okay, and then if it is there, you just assign this one to this result one, or you do that for the right subtree. So basically, you are recursing to the right and left subtrees, and then in the post order, you are evaluating the whole thing. So what it does is, if your Rx node is not null and Ry is not null, okay, so it means that you have already found, right?
Yeah.
Yeah, because both of the cases you are having a node, it means it is a common ancestor, and therefore you return from here. Or now in this case, you might have a situation where your root is equal to P, or root is equal to Q. Okay, so in that case, you will have to go and look further, right? If your Rx node is not null or Ry node is not null, then you can say, okay, yeah, this is my ancestor, correct? And then you actually return it from here. So this will be the most normal case, but in some cases, you might have one of the root itself as a P or Q, and the other node might be somewhere else, right? Okay, so your root itself is P. Okay, then you just have to look for Q. For that, you just have to explore the Rx or Ry. If they are not null, then you can say my current root, whatever it is, itself is a common ancestor. Okay, so that is one case. And in the second, the last one will be if my Rx is not null, okay, then you return this one, because that is obvious, right? So if
Yeah.
you have not found any of them, then at least whatever you have found, okay, there will be only one of them will be true, Rx or Ry. And that is the way you actually assign them. But in this case, it's going to be false because that won't be an ancestor. We need to have both sides. Yeah, it's slightly not so very easy to follow also, I would say. But that is what is an implementation here. And yeah, but I think there are many better ways of doing it also in lead code, right? And one
Yeah.
way was using an unordered map if you are allowed to use a data structure, correct? Yeah. Okay. So the last one, the problem is, I think we have very less time, but I'll just quickly run through that. So when we are done with this, so this is the checked subtree. Okay, so it says that we are given two subtrees T1 and T2. They both are binary trees, and T1 is much bigger than T2. And then we have to just create an algorithm and to see if T2 is a subtree of T1. So what does that mean? A tree T2 is a subtree of T1 if there exists a node in T1 such that the subtree of n is identical to T2, right? That is if the cut of the tree at node n, the two trees would be identical. Okay, so there are two approaches. One is a very simple approach, just convert the whole tree into an array, and then find it. But even though the time efficiency is n plus m, but it has a space also involved. And the other would be just without creating a array, converting it to array, and then you can do it in a different way. So I'll just quickly run through those two.
Compare the root, right? And then if it
Right, right,
matches.
right. Yeah. So this is the most easiest way of doing it. Okay. So here it starts, contain tree. You are given one tree node, two subtrees, T1, T2, and then you convert them into strings here like this. Okay. So you pass a T1 and then you serialize that to a string. And the same thing you do for T2. And then a subtree, you just try to compare both of them. If you have if you are able to find one of these, right, in this C++, you can go through the string function, and if you find, okay, if you have that substring already in it, so it won't return that n position here, then you can return true or else false. But I'm just trying to use some function to compare. But this is what the get order string does, right? So it goes to a node. Whenever you find a node is null, okay, then you and assign this as an x to just get that null, what you say, null node, right? So if any of the left and right trees are null, you actually always assign an x. So that is the way you serialize. So you don't lose some of those uh, way. Actually, when you are comparing, even if the structure is different, you still might get a valid string. In order to avoid that, you'll have to do it this way. I think we have seen it in other problems also in that one. Or else you keep on adding your node, and then you go to this left or right subtree. Correct? So that was an easy way of doing it. So, and the other way, as you mentioned also, is, just go through a subtree, T1 and T2, right? And then you go to the subtree, and if T1 is null, you return false. Or if both of them are same, then you can go and find if that tree, because you have to find, right, where one of them is true. Okay, whenever you find one node exactly the same, then you go and start matching tree. So you go through both of the subtrees together. Okay, and then you each and every node you find if they are same. If they are not, then you return false. Okay, so that's very straightforward implementation, right? Or else if you don't find it here, then you have to go to the pre-order, like you go to the left side also and the right side. Correct.
Both the-
Yeah, I think that was all I had for today.
So this is O of n only, right? Yeah, I think.
Well, I don't think
More
so.
than
It should be,
more than
yeah,
O of
more
n.
than n. Yeah, n by m, I would say, both sides,
Oh,
right?
sorry, mn. Yeah, yeah, yeah.
Yeah.
Okay.
So that what does it say? Yeah. So the earlier one was easy, but you have to do a serialization, right? You involve some space, and
Umani.
yeah.
On line 224, Santos,
Mhm.
you say match tree. Oh, match tree, not subtree. Okay, got it. Yeah.
Yeah. So you are matching both of these subtrees right here. Yeah. So this is super easy to follow also, right? Then this one I would say, not this one. Yeah. This is also easy. Yeah. Not a big deal. Yeah. Okay, but I had another tree problem. I think maybe I'll take that in the next session along with the next chapter. Okay, it is about the BST. We can find subsequences of it.